Today we will have a closer look at phenolphthalein, a famous indicator. Here we have the structure of phenolphthalein, while in the pH region of 0 to 8.3 it's colorless. Well, it's colorless because there is no extended pi system, just the aromatic rings isolated. But if we protonate this molecule, pH below 0, then it becomes red. What will happen? Protonating here at that carbonyl oxygen will lead to a ring opening of this lactone. Here we will have a cationic charge which is stabilized by resonance structures under participation of the aromatic rings and even participation of those OH groups. This is clearly a triphenylmethyl di, typical with a cationic charge. So, on the other hand, if we go to more basic environment, pH above 8.3, so then we have to assume OH will be there. It will deprotonate here the phenolic hydrogens, and if we have a phenolate here, it will deliver electron density. And again, the lactone will open up, but this time with the formation of a carboxylate and here a paraquinonoid system. So also a conjugated system. This has the color pink between 8.3 and above about pH 11. If we then go with a pH above 11, 12 and higher, it becomes colorless again. So clearly this conjugated system has to be interrupted, that it becomes colorless. We will have a change from an sp2 hybridization again to sp3, and this is the case if an OH minus reacts as a nucleophile here, restoring the aromatic system. Clearly this is colorless. And now a little chemistry riddle. Is there not another alternative mechanism to get to this structure? So again, sodium hydroxide, but this time attacking at the electrophilic carbonyl group, an addition elimination process, then we are already here with the OH group at that tertiary center, just deprotonating one of the phenolic hydroxyl group will give then that final structure for the indicator at pH above 12. Well, what we have here is essentially the basic hydrolyzation of an ester. So, as we know it from the production, for instance, of soaps. And this reaction usually requires elevated temperatures, for instance, reflux temperature of water, 100 degrees. Otherwise, it is a very slow reaction. Indicator, color change of an indicator, this even works at 0 or at lower temperature underneath 0 degrees. So clearly, since this is a typical indicator which works at very low temperature, this reaction pathway which is in need of higher reaction temperatures, well, we can just forget that and cross that out. Thanks for listening.